All right, section 2.8 is called endpoint and eigenvalue problems. And this just happens to be the last section in chapter 2, by the way. So this is the end of chapter 2. We're all done with chapter 2 after today. All right, so your typical endpoint and eigenvalue problems are going to look like this. Y double prime plus, well, I don't know, somebody give me a nice number. 3 or 2. How about 3y equals 0? And then we're going to have y at 0 equals 0, y at pi equals 0. Y at pi. So what makes these problems different from problems we've done in the past? Well, it's got a pi, that's true. That's not really what I was looking at.
Oh wait, that is both Y's.
Well, I don't see any eigenvalue there.
2 Y's instead of y prime?
The difference is, normally when I give you initial conditions, I give you y at 0 equals something, and then I give you y prime at 0 equals something. That's why these are called endpoint problems. I'm giving you conditions at two ends. Right? All right, well, how do we solve? R squared plus 3 equals 0. So R is plus or minus I square root of 3, not just 3I. You got to do square roots there, right? So Y is C1 cosine square root of 3x. Where's the cosine coming from? I got complex solutions, didn't I? Plus C2 sine square root of 3x. Now what? I plug in. Which one do you want to plug in first? 0. You like 0. All right, so 0 equals. When I plug 0 in, I get C1, and then I'm going to have cosine of 0. Cosine of 0 is 1. And then I'm going to have sine of 0. Sine of 0 is 0, so 0 equals C1. So my equation is reduced to y equals C2 sine square root of 3x. Now I plug in the other condition. I get 0 equals C2 sine square root of 3 times pi. What's the sine of square root of 3 times pi? Well, I don't know either. But what I do know for sure is that this is not the number 0. So if this is not the number 0, what's the number C2? 0. So C2 is also the number 0. It was a trick question. That's right. So what does that tell you about our solution? It's the trivial solution. The only way this can possibly happen is if y equals the number 0. Because I had 0 for C1 and 0 for C2, y is 0.
It's one big loop.
No, it's one big straight line.
Oh, yeah.
The only way it can happen is for the entire equation to be 0. So nothing's happening at all. No, it exists. It's 0. It's y equals 0. It's just a horizontal line. But it's certainly 0 at 0, and it's certainly 0 when you hit pi.
So are those, you said those are endpoints?
These are called endpoints, right? I'm giving you two conditions. What you can think of is you can think of a string. And so what I'm telling you is you're holding the string here. We're calling this position 0, and it's at height 0. And then you're holding the string a length of pi later. And we want to know if we have this differential equation, how can the string vibrate in order for the string to be 0 at 0 and be 0 at pi. And what we just proved is if we want the string to vibrate with this equation, what has to happen? The string can't vibrate. It just has to be taut and held straight across. It can't happen. You can't match this resonance, can't match that frequency. It's impossible. All right, let me change the equation ever so slightly, and we'll try again. What if I were to give you y double prime plus 4y equals 0, and the exact same initial conditions? Y double prime plus 4y equals 0, y at 0 equals 0, y at pi equals 0. So what did I change?
4.
Instead of the number 3, I wrote the number 4. It's the only thing I changed.
So it's still just going to be 0, right?
Well, we'll find out. This time we would have r squared plus 4 equals 0. So r would be plus and minus 2i. Our equation would then be y equals c1 cosine 2x plus c2 sine 2x. Same thing? Let's see, I plug in my first initial condition. I plug in y at 0 equals 0. That gives me 0 equals c1. Because cosine of 0 is still 1, sine of 0 is still 0. So I'm reduced to y equals c2 sine of 2x. Plug in the other initial condition. I have 0 equals c2 sine of 2 pi. What's the sine of 2 pi? 0. So this number here is already 0, which means what number can I use for c2? Any number I want. So how many solutions are there? There are an infinite number of solutions this time. So here, there are an infinite number of solutions. Is it because 4 is what? Is it because 4 is even? That would be an excellent question. Why did 4 work and 3 didn't? We'll answer that in a minute. So the solution this time is y equals c sine 2x, where c can be any number in the world you want it to be. In other words, what we're saying is, again, if you hold the string here at 0 and hold the string here at pi, and this time you have a 2x in here, which means your period is what? Your period is not 2, your period is pi. So what happens if you vibrate the spring, you get one complete cycle in a length of pi. And what does this number c change? The amplitude. So there's one correct answer. Another correct answer would be c could be a much bigger number, and you could have a wave that looks like this, but you would still have y at 0 equals 0 and y at pi equals 0.
No matter how hard you set the spring in motion, it's always going to be one complete rotation.
Correct. So no matter how hard you originally pluck that spring and vibrate it, it's going to make one complete loop and hit right there. All right, so now the big question is, why did 3 work? Why did 3 not work, but 4 did? And are there other answers? Would 5, if I used a 5 here, would I get an answer? If I used a 6, if I used a 7?
If you use the 5, you would get it to be 0, 0, because the square root will still be in there.
So that's your perfect root.
Oh, it has to be something with a whole root, right?
So our guess is it wasn't because 4 was even. I'm now hearing the guess that we're guessing that the square root of 4 turned out to be a nice number. It turned out to be the number 2. And that's our guess as to why that worked. And you're absolutely right. And those are called eigenvalue problems. So an eigenvalue problem would look like this. Find all non-negative values of, and they typically use that Greek letter. Which Greek letter is that? That's lambda. Lambda? Gamma? Lambda? That's lambda. Find all non-negative values of lambda such that y double prime plus lambda y equals 0 has non-trivial solutions. We already know one answer for lambda. We already know that one answer is 4. 4 is an answer. And we also know that 3 is not an answer. We know that for sure. So we know there are some answers, we just don't know how many. We're suspecting, from what I heard people guessing, is that we're guessing which numbers work for lambda? 1 with whole roots, which are usually called perfect squares. So we're guessing the answers are 1, 4, 9, 16, so on and so forth, the perfect squares. All right. So notice first it says, find all non-negative values of lambda, which means it's possible lambda could be which number? It can't be negative. Lambda can't be negative. So it says all non-negative values. So what's the smallest possible value for lambda? 0. 0 is non-negative, isn't it? All right. So typically with these, you start by assume lambda equals 0. And you try to figure out, could lambda equals 0 possibly be a solution? Well, if lambda equals 0, we have y double prime equals 0. How do you get y all by itself if you have y double prime equals 0? Do what? Take the integral. So y prime would be some number, let's call it a. And then I integrate again, y would be ax plus, I'm going to use letter b. I'm going to go in alphabetical order. You can use c if you wish. If y double prime is 0, then y has to be a linear function. That's correct. All right, so we take this and we try, I didn't give you our initial conditions. Our initial conditions are the same. Y at 0 is 0. Y at pi is 0. So we plug in our initial conditions and see what happens. All right, so we have, using y at 0 equals 0, I have 0 equals, a times 0 would be 0 plus b, which means b has to be the number 0. And then I plug in the second initial condition. I would have 0 equals a times pi plus b, but we already know b is the number 0. A has to be 0. So is lambda equals 0 a solution? No, because the only answer we got was the previous solution. Lambda equals 0 is not a solution. All right, so now next we assume lambda is a positive number. Lambda has to be non-negative, which means it either has to be 0 or positive. If lambda is positive, we have lambda double prime plus lambda y equals 0, which means our characteristic polynomial is r squared plus lambda equals 0, which means r is plus or minus square root of lambda I. Right, because we'd have to subtract lambda. Since lambda is positive, when we move the lambda over, we've got a negative number over here. That tells us our solution would have to be the form y equals c1 cosine square root of lambda x plus c2 sine square root of lambda x. We plug in our first initial condition. When I plug in y at 0 equals 0, I get 0 equals c1 still. Because cosine of 0 is still 1, sine of 0 is still 0. Which means my equation has to have the form y equals c2 sine square root of lambda x. Finally, I plug in my other initial condition. That would be 0 equals c2 sine square root of lambda times pi. Now, what do I want to have happen? Do I want c2 to be the number 0?
No.
No, what happens if c2 is the number 0? Then I get the trivial solution, and then we don't have anything. So what I want is I want sine of the square root of lambda at pi to equal 0. So the question is, which numbers can I plug in for lambda? Well, lambda could be the number 1, because what's the square root of 1? 1. And the sine of pi is?
Well, it could be any whole number.
No, it can't be any whole number. It can't be 2. For example, if I plug in 2, I get the square root of 2 times pi. What's the sine of the square root of 2 pi? I don't know, but I know it's not 0. So what's the next number I can plug in for lambda? 4, because the square root of 4 would give me 2. I would have sine of 2 pi. Sine of 2 pi is 0. So the next number I could plug in is 4. The one after that, 9, 16, 25, on and on and on. So your guess as to what are the answers is correct. The answers are the perfect squares. Okay, so these answers that you get, these things, these are called the eigenvalues. And then y equals sine square root of lambda x is called the eigenfunction. Questions on that? What's that? What do we do with it? All right. So the question is, what does this mean? What is this good for? Well, I want you to consider, once again, having a string where you're holding it at length 0 and you're holding it at length pi. What we just discovered is if you pluck this string and start it to vibrate, one of the answers you're going to get is y equals sine x. If I graph y equals sine x, what does that look like? It goes up and down like a sine wave. Yes, yes. What's its period? No. Not pi. You're getting closer though. 2 pi. Its period is 2 pi. So it goes up and it comes back down and it hits right there. And if you kept going, it would go down and back up. We also just discovered that another solution, another vibration you're going to get is y equals sine of 2x. What's the period of y equals sine 2x? Pi. So you're going to get one complete cycle.
Oh, it compresses it. It infinitely compresses.
Well, that didn't quite work out because that's supposed to be halfway in between, but you get the idea, you get one complete cycle. We get another solution. Y equals sine of 4x, which has a period of pi over 2. So there you're going to get 2 complete cycles. so on and so forth. So what does this have to do with anything?
Well, kind of looks like the Pepsi logo.
Kind of looks like the Pepsi logo. That's a happy accident. That's true, though. It does kind of look like the Pepsi logo. What else does it have to do?
They can increase your frequency by just changing that number.
True. You can change your frequency, which does what? Any musicians? Anybody play piano?
Yep.
Okay. Not primarily, but you know how a little bit about playing piano. On a piano, there's two pedals, sometimes three, usually two. What do the two pedals do?
Hold out a note and transmit.
Okay, one's the dampener. The one on the left is the dampener, known as the sostenuto. Fancy Italian word. What does that do? Anybody ever look inside a piano and see what it does?
It takes the
It takes the hammer and like pulls it to the strings so that when you pluck it, it's not as loud.
If you ever look inside a piano, for each note, there's usually actually 3 metal strands. So when you hit the key, there's a hammer that comes up, hits all 3 strands and plays the notes. And it also lifts the damper off. So when you hit the key, the damper comes up, the hammer hits the 3 strings and makes a sound. That soft pedal, what it actually does is it usually shifts the hammers all over a little bit, so that now when you press the key, the dampener comes up, the hammer only hits one of the 3 strings. And that's why it sounds quieter. You're getting 1/3 the volume. Okay? What's the other pedal do? No, I'm sorry. The pedal on the left is called the una corda, because you only hit 1 string. The pedal on the left is una corda, 1 string. The pedal on the right is sostenuto. What's the pedal on the right do?
Lifts the dampers right off.
It lifts all the dampers. So when you hit that middle C, what happens?
It'll keep loud. It'll keep playing.
Okay, the dampers are all up, so the hammer will come up and it'll hit it, and it plays a middle C. But you told me it's louder. Why is it louder? Resonance. What do you mean resonance?
Resonates with the
The strings will continue to
When you hit that middle C, what happens is you really don't get just one frequency. You get multiple frequencies in the pattern 1, 2, 4, or some other pattern. And so what happens is this vibration here might be the vibration for the middle C. But this next vibration is the vibration perhaps for a C 1 level up. So since all the dampeners are up, when that middle C starts to vibrate, it vibrates at the middle C frequency. It also vibrates at the octave up 1, which causes the string an octave up 1 to start vibrating, and you get noise out of that one also. Which then causes another frequency with the 4 pi, the string up. So when you push middle C, you don't just get middle C, all the C's on the keyboard play. That's why it sounds louder. You're getting a resonance. It makes all of them. It actually does even more than that. Some of these frequencies that you get when you push middle C are not just middle C. You also get what are called the harmonics. What are the harmonics for middle C? Good music theory class today. What are the harmonics? Typically, they're the perfect 4th and the perfect 5th.
Yeah.
So it'll be F.
F and G. So not only are all the C's vibrating, suddenly all the F's and the G's start to vibrate too. And that's why you get a richer, fuller sound when that sostenuto pedal is pushed. When you play one note, you're getting much more than one note. That's why it's louder, and that's why it sounds more full. Because that's what's happening. Okay?
Yeah.
What happens if you have an electric piano? Well, then it's all coded into the piano to try to emulate the same sound you really get.
Depends on how high quality.
Depends on the quality of the piano. You get the exact same situation with the guitar. When you pluck one note on a guitar, you don't just get one note. because you get multiple resonances, which causes the other strings to also vibrate, and you get multiple sounds. So that's what's happening here. The other thing you can think of is if this is a beam that's held on each end and people start to jump on it, you don't just get the one frequency, you actually get multiple frequencies. Now one of them, the one jumping, the pattern that they're jumping in, gives you the biggest frequency, but you also get sub-frequencies within it.
Like on a trampoline kind of.
Like on a trampoline kind of, if you ever watch a trampoline, you get the big bounce, but there's also little ripples going on within it, and that's the resonance that you get from the other waves that are solutions to the differential equation.